Okay, I'm going to derive the basic gas laws from PV equals nRT. Now, this is the one need to know equation. If you know any equation, though, PV equals nRT. Okay. Now, in deconstructing this, I'm going to kind of reverse engineer it. Okay. Solving for the gas law constant, if I say R is equal to PV over NT, okay, if this was under one condition, because this is a constant, I could say that R also equals PV times NT under a second condition. Now if I make these, by transitive property equal to each other, I can just cancel out the R's, and I can come up with what they call the universal gas law. This works under all conditions. The variables in it are N, T, P, and V. So you have 4 variables. And the universal gas law becomes P1 times V1 over N1 times T1 equals P2, V2, N2, and T2. So that would be true of any gas in any condition. Now, if I say that I'm in a closed container, a balloon or a sealed cylinder, in a closed container, the moles would be constant. You wouldn't be able to then, if you kept the number of moles in the balloon constant, if it was a sealed balloon, you'd get this effect. If moles 1 equals moles 2, then you can take your universal gas law and if I multiply both sides by N1, the N1 and N2 cancel out because they're the same. And you arrived at what we call the combined gas law. Now, this would be the second law, which I normally tell people to memorize. If you're going to know any gas law other than P equals nRT, know your combined gas law, and they're all other laws are easily derived from combined gas law. So I get P1 V1 over T1 equals P2 V2 over T2. And then when you're doing a problem, it's easy as making a list of all your variables, figuring out which one you don't have for, solve for that one, and then you're good. In combined gas law, moles equals a constant. Now I'll use this as a launching point for my next set of gas laws. Okay, and again, this is the reverse of how these gas laws were actually discovered. I'll make sure that I'm centered here. Okay. All right. So let's see. If I start off with combined gas law, P1 V1 over T1 equals P2 V2 over T2. Okay. The first gas law that I'll derive is Boyle's law. This will be number 1. Now, if you know this gas law, you can easily derive Boyle's law. I always tell students to remember boiling water happens at a constant temperature, 100 degrees Celsius or 373 Kelvin. So temperature is a constant. Don't want to mix that up with Kelvin. So if temperature is a constant and moles is a constant, you start with combined gas law. Under this condition, T1 equals T2. So if I multiply both sides by T1, it cancels out on the left, and because they're the same, it cancels out on the right, which leaves you with Boyle's law. P1 V1 equals P2 V2. Effectively, what Boyle discovered is that pressure times volume is a constant number, K. That K being constant, not Kelvin. Okay. This finds out that they're inversely proportional. Boyle did his work in the late 1700s. This is at the age of enlightenment. So he was looking at pressure versus volume, and as one comes down, the other goes up. So to maintain this, if pressure comes down, then volume goes up. And so that looks like that hyperbola. As volume goes down, as volume comes down, pressure would go up to maintain that constant number. So that's an inverse proportionality. Okay. Second gas law. This is after Charles. I believe Charles was Scottish. And I like to think of an ex-76ers basketball player, Charles Barkley. He was always under constant pressure. Or if you're an old TV fan, you can say Charles in Charge was under constant pressure and constant moles. Again, to derive this, we would start off with PV over T, P2 V2 over T2. And if we have constant pressure, the pressure would cancel out. So P1 equals P2 for constant pressure. Okay. And then Charles's law ends up being V1 over T1 equals V2 over T2. Okay. And what Charles discovered is that V1 T1 was a constant. This is a direct proportionality. So if I graph that, temperature versus volume goes down to 0. Now, here's where we got the Kelvin scale coming in and the fact that we can't use Celsius. Because the coldest temperature Celsius is negative 273. And freezing water is just 0. So we have a whole range where we're in the negative and we have a 0. If Charles took data up here, which he did, and his work looked just like this in the 1800s, it was perfect. He extrapolated. He went outside the data, and when you come down to it, he found that at 0 volume, your temperature was, that's how he set absolute 0. So absolute 0, volume is equal to 0, and your molecular motion is equal to 0. So that's the coldest temperature you can get, 0 K, which is equal to negative 273 Celsius. Well, if you take into account negative numbers, if you're trying to apply Charles's law, negative numbers would get you negative volumes, which don't exist, and that's why he realized he had to set a base value of 0. And truly, when you plug 0 in here, it goes to undefined. Okay, and that's why absolute 0 is more of a theoretical concept, but maybe you would be in a black hole. But that's Charles's law. Okay, next law. Okay, always starting off with my mind on the combined gas law. And we have the third law, Gay-Lussac. Gay-Lussac looked at this and he said, let's do constant volume. And again, moles would be constant. Okay. And if I start off with P1, V1, T1, P2, V2, T2, and a constant volume V1 equals V2. So if I divide both sides by V1, now V1 and V2 cancel out because they're equal. So I get Gay-Lussac's law. And you get P1 T1 equal P2 T2. And when you're applying these, you really don't have to know whose name they are. You just have to know which variables are constant. P1 T1 is a constant. Again, if you graph this, when you come down to zero pressure, you got 0 degrees Kelvin, K, and it's a straight line. All their work would have been up here around 0 degrees Celsius and maybe 23 degrees room temperature. And if you extrapolate, that's where you can figure out what absolute zero is, and that's when you can find out what the air pressure is. You can get that from Boyle's law too. Okay. Fourth law I'll show you is Avogadro's law. They don't show this a lot in the textbook, but I think there's one interesting thing to tell you about Avogadro's law, and that's this. In Avogadro, he said, well, let's make constant pressure and constant temperature. So he said P and T. Now, he went back to the universal gas law, P1 V1, N1 T1 equals P2 V2. And said one thing, my hand said another. V2, N2 T2. When pressure 1 is constant, we'll cancel that out. And when temperature is constant, we'll cancel temperature out. T1 over T2, so T1 equals T2. And P1 equals P2. So they'll cancel. And then you get Avogadro's law. V1 over N1 equals V2 over N2. And the interesting thing of showing this is that when you look at the constant,